Welcome to The Explainer. Today, we're going to dive into one of the most important stories in AI, how we taught machines to remember. This one idea, this one breakthrough, is really what took AI from being kind of forgetful to the near genius we see today.
Okay, so let's just jump right in. We are surrounded by this stuff, right? Every single day. You ask a chatbot a question, you translate a menu in a foreign country, you get a quick summary of a long email. All of these things feel like magic. But how in the world did we actually teach a machine to understand something as messy and complicated as a human sentence?
Well, the core idea behind all of these tasks is something called a sequence-to-sequence problem. It sounds technical, but it's super simple. You're just taking one sequence of things, like a sentence in English, and teaching a model to turn it into a different sequence, like that same sentence in Urdu. That's it. This one concept is the foundation for so much of what we call language AI. But that brings up a huge problem, right? A sentence isn't just a random bag of words. The order is everything. The meaning of a word totally depends on the words that came before it. So the real question became, how do you build a network that can actually remember the past? How does it hold on to the beginning of a sentence so I can understand the end?
The first really brilliant attempt to solve this was something called the recurrent neural network, or you'll just hear it called an RNN. It was this special architecture designed from the ground up to work with sequences, where what happened a moment ago is crucial for understanding what's happening right now.
And the way it worked was actually beautiful in its simplicity. It's basically a loop. The network reads the first word and creates a tiny little piece of memory from it. Then, when it moves to the second word, it looks at that new word and the memory of the first one. It combines them, creates a new memory, and passes that on. Step by step, it builds a memory of the sentence so far. It's a fantastic idea. I mean, in theory, it should work perfectly. It should be able to remember the context of an entire book if you let it run long enough. But, and in science, there's always a but. This elegant solution had a massive, critical flaw. And that flaw has a very technical-sounding name: vanishing gradients. But honestly, the best way to get it is that game of telephone. You know where a message gets whispered from person to person? That's exactly what was happening inside the RNN. The memory, the signal of what happened at the start of a sentence, would get weaker and more distorted with every new word it processed. By the end of a long paragraph, the memory of the beginning was just gone. And this right here shows you what that actually looks like in practice. You take this pretty long sentence. The correct summary needs to capture both the early problems with funding and the final success. But look what the RNN does. Because its memory fades, it completely forgets about that first part. It only remembers the most recent thing it saw, that the project was a success. It loses all the important nuance. So you can see this was a huge problem, a massive roadblock. It meant that for any really interesting, long-form text, RNNs just weren't going to cut it. And so the entire field became obsessed with the next big question: how do you build a network that has a better memory?
And the answer, when it came, was an absolutely ingenious upgrade. It was called the Long Short-Term Memory Network, or, as everyone calls it, the LSTM. And it was designed for one specific purpose: to solve this exact forgetting problem.
So what is an LSTM? Well, you can think of it as an RNN 2.0. It's got the same basic looping structure, but it adds two game-changing new parts. First, a dedicated memory lane called the cell state. And second, a series of gates that act like intelligent traffic cops controlling what information gets to go into and out of that memory.
This conveyor belt analogy is honestly the perfect way to picture it. Imagine the regular RNN process is the main assembly line. The LSTM adds a whole separate conveyor belt that runs alongside it. This belt is the long-term memory. Important information can be placed on the belt and just cruise along, untouched, for as long as it's needed.
And here is where the real magic happens: the gates. The forget gate is a little controller that looks at the old information on the conveyor belt and decides, you know what, we don't need this memory anymore, and it removes it. The input gate looks at new information coming in and decides if it's important enough to be placed onto the memory belt. And finally, the output gate decides which of those long-term memories on the belt are actually useful for the task it's doing right now. It's a completely dynamic, intelligent memory system.
So when you put them side by side, it's crystal clear. The RNN is simple, but it has a terrible memory. It just forgets things. The LSTM, okay, it's more complex and it takes more computer power to run, but its smart, gated memory system lets it handle those really long, complicated tasks that were impossible before.
So what's the big takeaway here?
This jump from a simple fading memory to a smart, gated one wasn't just some small incremental improvement. It was a massive leap forward. It was a complete game changer that unlocked the potential for AI to finally understand complex human language.
And I mean this literally. This single innovation is why the tools we use every day work as well as they do. It's why machine translation can handle complicated sentences, why summarization bots can read a whole article, and why chatbots can actually hold a coherent conversation. For years, the LSTM was the absolute engine, the workhorse behind almost all modern language AI.
And that leaves us with a final, really fascinating thought. Solving this long-term memory problem with LSTMs was a huge, monumental achievement. But in science, every great answer just leads to an even bigger question. And this breakthrough opened the door to a wild one. What happens when memory isn't just about the past? What if a machine needs to understand complex relationships from a million different places all at the same time?